Hi there, Andreas Aragoneses here to continue with our classical mechanics course. Let's study parabolic motion. When there is no air friction, the equations of motions are an old friend of yours. Where here I consider g as 9.8 meters per second squared, positive is up and to the right, the initial velocity decomposed into x and y axis. To find the time of flight, we impose that delta y is equals to 0 and solve for t. We find two solutions, t equals to 0, which is the starting point, and t equals to 2v0 sine theta over g. To find the range of flight, how far the object will get, we substitute this result of time into delta x. We use the trigonometric identity that 2 sine alpha cosine alpha is sine of 2 alpha, and we get delta c equals to v0 squared sine of 2 theta over g. We see that the range depends on the initial velocity, on the angle, and on the planet where you are. We can find what is the angle that maximizes this distance. What is the angle at which we need to launch the object if we want to reach as far as possible. To do that, to maximize a function, we derive and make the derivative equals to 0. Because we want to maximize the function with respect to the angle, I will derive with respect to theta. This gives us that the angle is pi over 4, so 45 degrees. But all this I just did is kindergarten physics. Let's do some more realistic thing. Let's consider air friction. In this case, we have friction on both the x and the y axis. So now we write Newton's laws as minus mkvx equals to mx 2 dots and minus kvy minus mg equals to my 2 dots. If we want to describe the motion of the ball, we need to find x as a function of time and y as a function of time. Let me first solve the first differential equation to find the x position as a function of time. Remember that the velocity is x dot and the acceleration is x 2 dots. Masses cancel and we integrate once to find v sub x of t. Velocity on the x-axis is not constant anymore, as we could expect, because air is working against the motion. The ball will stop eventually. I integrate again to find x of t. The ball tends asymptotically to a final position. Let's work now on a y differential equation. I'll follow the same steps as for the x-axis. I'll integrate twice to get first phi of y and then y as a function of t. Remember that unlike dropping an object from a certain height, we have a non-zero initial velocity this time. So this is the y position as a function of time. Now we have the equations of motion for both axes. Okay, what if we're interested in the time of flight and distance range, as we were in the case of no air friction? As before, we impose that delta y is 0 and solve for the time t. But we can't do it analytically. There isn't one. So as soon as we introduce some irregularity to the spherical cow in the vacuum, we start to find issues such as no analytical solutions. So here we need to use a different approach, the perturbation method. This method approaches the solution step by step. For this method, we need to use a parameter, the expansion parameter, that can be considered as small, and then write the time of flight as a function of this parameter. Of course, the larger this parameter, the longer the expansion and the more wibbly-wobbly timey math involved. Let's go back to the equation of the time of flight we just found. We're going to consider small values of the friction constant k and make expansion in series of Taylor of the exponential, which is where we have the time dependence. This way, we'll be writing this equation in polynomials. We'll solve for t and have an approximate expression for this time of flight with air friction. For the series expansion for the exponential function, we have, so for the time of flight, because I'm considering a small k parameter, I'm going to truncate the function at terms of k to the cube.
And I move the k squared dt term to the other side.
We get that t is equals to 2v over g plus kv plus k over 3t squared. But remember, we wanted to write this as a polynomial in terms of the parameter k. But because k is in the denominator, we needed to expand this fraction. Now we have the time of flight as a polynomial expression in terms of k. But this result still has the time of flight as a function of time of flight. For k equal to 0, we recover the case without air friction. T0 equals to 2 times the initial y velocity over g. Now it's when the perturbation approach comes into play. We substitute the k equals to 0 solution into the approximate equation.
So T1 equals to 2v over g times 1 minus kv over 3g, which is an approximated result for when the time of flight when k is very small.
This for the time of flight. For the distance traveled, we need to get back to the delta x equation. We, again, write the expansion in series of Taylor. Do a bit of wibbly-wobbly mathy stuff. And find the approximate distance traveled in the presence of air friction, but not too much air friction, which happens that can be written in terms of delta x naught, the solution without air friction. So we see that just as we try to solve more realistic problems, we face some issues. There are no analytical solutions. But we have our other approaches, other tools. The perturbation method allows us to find good enough solutions that can be as accurate as we want to. And at the end of the day, we don't need solutions with infinite resolution, as our experiments have associated experimental uncertainty. We don't need more precision than the experimental resolution. We could also use a computer to find these solutions. At some point, this wibbly-wobbly mathy stuff can get quite nasty. May the science be with you.